Hi, welcome back. In this week, we will study the concept of the Markov decision process on which the reinforcement learning is based. And then take a look at one of the reinforcement learning algorithms briefly. So in today's sessions, we briefly go over what the reinforcement learning is, and then we try to understand the basic components of the Markov decision process and take a look at one example for helping you better understand the Markov decision process modeling. And finally, we explore the solution approaches for the final horizon Markov decision process. So let us briefly go over the classification of the machine learning algorithms. From this course, you first learn the supervised learning. As you know, these supervised learning models assume to have the target to predict, and from the data consisting of inputs and outputs, we try to learn the relationship between the inputs and the outputs. On the other hand, unsupervised learning algorithm assume to have so-called unlabeled data, and we try to, the algorithm try to find out some kind of the underlying patterns or groups in data. So unlike the supervised or unsupervised learning, the paradigms of the reinforcement learning deals with some kind of the learning in the sequential decision-making problems in which there is limited feedback. And from this, we wish to attain a goal. All right, so the reinforcement learning is a general class of the algorithm in the field of the machine learning that aims at allowing the agent to learn how to behave within the environment, where the only feedback consists of the scalar value called a reward. The goal of this agent in the environment is to perform the actions that maximizes the rewards in the long run. So let's take a look at this figure. And there are agent and the environment. And it shows some kind of the interactions between them. The distinction between the agent and environment might not be always clear or intuitive. And you could think that everything the agent cannot control is considered as the part of the environment. So for example, let's think about a motion control of a robot. Although the motors of the robot agent might be considered as a part of the agent, the exact functioning of them in the environment is beyond the agent's control. So the agent gives the command to the gear up or gear down, but their physical realizations can be influenced by many factors. So the environment is something around the agents which cannot control. And the changes over time through the interaction with the agents. So as shown in the slide, the perceptions the agents get from this environment are the environmental state, right? And the agent can choose an action in each state, and after each action is performed by the agent, right, this action, and the agent receives some kind of the reward, right, the reward, and the action for the certain state lead to the another state in the environment. In the reinforcement learning, the agent learns from the series of such interaction with the environment and adjusts their actions to choose at each step. In fact, the reinforcement learning has a long history, and there are many real-world applications of the reinforcement learning, such as the IBM Watson's Jeopardy and this Otter game right? Archer game by the DeepMind. And the famous AlphaGo, also by the DeepMind. So those are based on the reinforcement learning algorithm. And it is known that this algorithm, along with the deep learning, is a deep Q-learning, for example, may have a lot of potential applications such as robotics, computer networking, vehicular navigations, and so on. All right, so we now discuss the Markov decision process, which is the mathematical framework for defining a solution in the reinforcement learning scenario. And the Markov decision process is defined as the stochastic process, along with the decision maker that observe the process and is able to select the actions that influence the development over time, of the process over time. All right? Along the way, so the decision maker receives a series of the rewards, and that depend on the both actions chosen and the states occupied by the process. So this framework is what the reinforcement learning assumes. All right, so a Markov decision process can be characterized mathematically by a collection of the following 5 components. So 1, 2, 3, 4, and 5. And let's take a look at one by one. All right, so the first component is T, which is a set of the stages or decision epochs. Decision epochs are the point in time when the decision maker decides and executes on actions. So we mainly consider the Markov decision process with the discrete T, which means the element of T are finite. So you can say T is equal to 1, 2, up to n. That means this is the finite, or countably infinite. So that means T is 1, 2, up to infinity. So these are examples of the set T. And T can be either finite or infinite. If T is finite, we assume that in the last stage, for example, this stage, no decision will be made. All right. And a Markov decision process is said to have either finite horizon or infinite horizons, respectively, depending on whether the upper bound of the set T is finite or infinite. So this is the case of the finite horizon, and this is a case of the infinite horizon. All right. The second component is S, which is the set of the states, or we call state space. So each state in a system or the environment represent the status of the system, and decision maker can observe, right? And in the discussion, we consider the case that S is a discrete, right? So you can count, and you can count, for example. All right, the third component is A with subscript S, which is the set of the action or action space that are the collection of the actions the decision maker can choose when the system is in state S. So the A refers to the set of the all possible actions. All right, so the fourth component is the transition probability. As you remember, when we study Markov chain or Markov process the last session, we learned the one-step transition probability. At the time, the one-step transition probability refers to the conditional probability of the immediate next state given the current state. So in the Markov decision process, we also have this similar transition probability. Depends on not only the current state, right, but also the action decision maker takes. In that, this transition probability specifies how the state of the system changes one decision epoch to the next. Right. So as you see from this figure, so let's say the system is in a state S at stage T, right? Depending on the action chosen, the probability of the state in the next stage may be different. So for example, so if the decision maker chooses A1 as an action given the current state S, the next state becomes S prime with the probability of 0.8, right? And the S triple prime with the probability of 0.2. On the other hand, for the same state, if the decision maker chooses A2 as an action, then the next state becomes S prime with the probability of 0.1 and S double prime with the probability of 0.6 and S triple prime with the probability of 0.3. Right? So that is the concept of the transition probability. So you should remember that this transition probability depends on not only the current state, but also the action the decision maker chooses. All right, the last component. The last component is the reward RT. As you see, the reward is the function of the current state S and the A, which is the action decision maker chooses at the decision epoch T. So as a result of the choosing a certain action A when the system is in state S at the time or stage T, the decision maker receives some kind of the reward, which can be either positive or negative. Right? And for the finite horizon Markov decision process, as already mentioned before, no decision is made at the last stage, right? Last decision epoch. And hence, we additionally define a reward which only depends on the final state of the system. So we call such the reward as the terminal reward. All right, so given those 5 components of the Markov decision process, we can decide a decision rule and a policy, as like we discussed in the lecture of the dynamic programming. As you may recall, a decision rule, delta t, is a function of the state S that maps from the state space to the action space. So it tells the decision maker how to choose the action to be taken given the state S at the decision epoch T. So you can think about like, you have some kind of the mapping table, right? Mapping table. And this part, you state the all possible actions, let's say all possible state, 1, 2, 3, and so on. So these are some kind of the sets, the states, right? And in the mapping table, you also have the action to choose for each state. Let's say when the state is in S, you can choose the action to move to the right. Action 2, let's say the action, the decision maker need to choose should be go down, and so on, right? So it shows that the action you should choose for each state, right? That is the decision rule. So in the case, this table itself is a decision rule, right? And the policy pi is a sequence of the decision rules for each stage, right? And in the next sessions, we will talk about some kind of the stationary policy, and that means we have the same decision rule in every stage or decision epoch. All right, finally, we can define the value function Vt, which is a function of the state St. So we call this recursive equation as the Bellman optimality equations. So the value function indicate the maximum total expected rewards starting in the state St from the stage T onward. So from the T to the end. So let's say if the state is we have the final horizon in the Markov decision process, right? So the value function is expressed in the recursive manner, right, as presented in this slide. So what the recursive equation means is at each decision epoch T, we are in the state St, and we are interested in finding the action At that maximizes expected total rewards, which can be expressed as the sum of the expected immediate reward by taking action At when the state is St at the current stage, and the expected maximum total remaining rewards in stage T plus 1, T plus 2, and so on up to the final stage. So we call this term as expected maximum total reward to go. So you can think of the value function expressed in the recursive manner when we discussed the dynamic programming last week. The value function of the Markov decision process is very similar to one from the dynamic programming. The only different term is the second term, right? Instead of the deterministic maximum reward to go function of the next state, we consider some expected maximum reward to go. Okay, so in this slide, we illustrate this Bellman optimality equation with this example. So the value of the Markov decision process of the state S in a stage T is VTS. And this represents the maximum total expected rewards from the stage T to the end, right? And let's say at the current state S, we have the two actions available, A1 and A2. A1 and A2. And according to this transition probability, we know the next state at this stage T plus 1 with corresponding probability. So for example, given S, if we choose the action A1 with this probability, S prime become the next state. And with this probability, S triple prime becomes the next state from S. So we can calculate the maximum total expected reward from this stage T onward when the decision maker chooses the action A1 as the reward, immediate reward, plus the expected value of Vt plus 1. So for example, so you should consider you will receive, so Vt plus 1 represent some kind of the maximum total expected rewards from this state, in this state S prime, from the stage t plus 1 to the end, right? So you receive the immediate reward, and as with this probability, you will be in the S prime in the next stage, and you can think about the expected total remaining rewards from the stage t plus 1 to the end. And corresponding probability is Pt S prime S A1. And plus, with this probability, next state at this stage t plus 1 is S triple prime, and you can consider the expected total remaining reward from the stage t plus 1 to the end. So that is Vt plus 1 S triple prime, and the corresponding probability is Pt S triple prime given that S A1. Right? So you can also calculate the maximum total expected reward in S from the stage T onward when the action A2 is chosen. So similarly, so the expected total reward from the stage T, from S in stage T to the end is equal to when the action A2 is chosen. So immediate reward, and you should consider the expected total remaining reward from the stage T plus 1 to the end. And you will receive this remaining total expected reward with the probability of this. So Pt S prime S A2, and plus you will have this one Vt plus 1 S double prime with the probability of this. So Pt S double prime given that S and A2, and plus this one, right? Vt plus 1 and triple prime with the probability of this, right? So Pt as triple prime given that as A2, right? So you have this one and this one, and we try to take the maximum among these two values, right? Okay, so you choose the either A1 and A2 that maximizes this value. So you should compare this value and this value and try to take the bigger one. That is the value of the VTS. All right? So we now take a look at an example to better understand the modeling of the Markov decision process. Suppose that a manager of the warehouse is responsible for maintaining the inventory of the single product. So he orders the additional stock if needed at the beginning of each month. The manager wishes to maintain a sufficient stock to fill the random number of orders that will arrive each month while maintaining the total cost, while minimizing the total cost, including the ordering cost and the inventory holding cost. right? So here are several assumptions of this problem. So stock is ordered and delivered at the beginning of each month, right? And demand arrives throughout the month, but the orders are fulfilled on the final day of the month. So for simplicity, for simple calculations. And if demand is larger than the inventory on hand, any unfulfilled orders are lost. So we simply fail to satisfy the customer demands. And the revenue, cost, and demand distributions are constant over time. And finally, the warehouse has the maximum capacity of the M unit. So the maximum number of units in the warehouse is equal to M. So we have the several notations used in this example. So ST is the number of the unit in the warehouse at the beginning of the month T. So it can be the state of this problem, right? So manager take a look at how many units are remaining, So they take a look at. So that is some kind of the status of the environment, and it can be considered as the state, right? And AT is the number of unit order to the supplier at the beginning of the month T. So that can be considered as the actions the decision maker, in this case the warehouse manager, needs to choose, right? And DT is the number of the random demand during the month T. So PJ represent the probability that demand at the month T is equal to J. And K is the fixed ordering cost. It incurs when you place an order. CU is the variable ordering cost when ordering U units. All right. So the variable ordering cost increases proportionally as the number of ordered unit increases. So OU is the cost of the ordering U unit. So you can think about OU in this way. OU. So if you order greater than 0, you should pay the fixed ordering cost and the variable ordering cost as well. So CU, all right? And if you order nothing, then the OU is equal to 0 because you don't necessarily to pay any money, right? Because you did not order anything. And HU is the inventory holding cost, or cost of the maintaining an inventory of the U unit for a month. And FJ is the revenue earned from selling J unit of the inventory, right? And the FU is the expected present value at the beginning of the month of the revenues earned throughout the corresponding month with the U unit of the inventories. So basically you try to calculate the expected revenue. And the revenue depends on the demand and how much I have. So in this case, a U unit. So you can consider two different cases. If the demand is less than U, you can only sell the number of unit which is equal to the demand. So let's think about FU. If when demand is less than U unit, right? So let's say up to U minus 1. So this is the case that demand is less than U unit. Then you will earn this amount of revenue because you can only sell J unit and with the probability of this one, right? So demand is equal to J. And if demand is greater than or equal to U unit, because you only have U unit on hand, even if demand is more than U unit, you can only sell U units. So that is the revenue you're going to earn in the case when the demand is greater than or equal to U unit, and you should multiply by corresponding probability. So that is the kind of the expected revenue, FU. All right, so the MDP of this problem can be formulated as follows. Let's say decision epochs. T is equal to months 1, months 2, and so on, and up to, let's say, assuming that, we have the finite horizon Markov decision process. So each value, each element in this set T corresponds to the each month, right? All right, the state. So we can use the number of the unit in the warehouses at the beginning of each month, and we can consider it as a state of the system. So then, what is the possible value of the number of unit in the warehouse? So I would say 0 can be possible because there's nothing in the warehouse. 1 can be possible, right? And we can have m number of units. So m can be possible. But m plus 1 cannot be possible. Why? Because the warehouse capacity is equal to m. So the state space becomes same as this, right? Right. So the action in this problem, AS, is the set of the number of units to order at the beginning of each month when there are S number of units in warehouse at the beginning of each month. So, right? So that S is the number of units in the warehouse. Then the manager can order 0 unit, right? 1 unit, 2 unit, up to how many? M minus S unit, right? He or she cannot order more than that. Otherwise, the total number of units will be above the warehouse capacity M. So the state space AS becomes this set. Right? And we now define the transition probabilities or this conditional probability. Okay? So I will define PTJ given as NA. Right, so in this case, J refers to the number of units in warehouse at the beginning of the next month or T plus 1 month. So we can consider 3 different possible values of J. So you need to specify all possible values of J. So J is belong to this state space. So let's think about this is the possible value of J, and it can be 0, it can be 1, up to M minus 1 and M. So that is the possible value of M, and you can consider the transition probability given S and S. S and A. So let's think about this is the S plus A. All right. So let's think about the case that J is greater than S plus A. So let's say these values. Suppose that J is greater than S plus A. Well, it is impossible to have such J. Why? After manager received the new order, total number of units on hand becomes S plus A, as you know. So the number of units at the beginning of the next month cannot be larger than S plus A. So the corresponding transition probability becomes 0 if J is strictly greater than S plus A. So this conditional probability is 0. And let's think about the second situations, right? So let's think about the situation that J is in between 1 and S plus A. So if J is greater than or equal to 1 and less than or equal to S plus A. Right? So in that case, the J, so in this situations implies that the demand and the month T was S plus A minus J. Right? So that means S plus A minus J units are sold in month T. Right? So this conditional probability when J belong to this condition is equal to the probability that demand is equal to S plus A minus J, or P, small p, S plus A minus J by definition. All right, so let's consider that J is equal to 0. That means you sell on-hand inventory S plus A all. So this is equivalent to the situation that demand is greater than or equal to S plus A. So this transition probability is equal to probability that demand is greater than or equal to S plus A. Or you can say J is greater than or S plus A up to infinity Pj. Right? So that is the transition probabilities in this case. All right. So how can we formulate the reward? So reward RTSA is the expected immediate reward. And in this example, the reward must be the expected profit earned in the month T. So since the expected profit is equal to expected revenue minus ordering cost and the holding cost, so RTSA is equal to expected revenue when the on-hand inventory is equal to S plus A, right? And the ordering cost, you order a unit and you hold S plus A throughout the month T, right? And if this problem has the final horizon, so let's say N, the as the last stage, so we should additionally define so-called terminal reward, Rn, and this terminal reward only depends on the final state, say S, right? So if I say, GS is kind of the salvage value or scrap value at the end of the last stage, so I would say this terminal reward RNS is equal to the GS, for example. Right? All right, so we now talk about the policies. So you may introduce a lot of policies. And you can define a policy in the form of the so-called table. So let's say, right? So you can decide the table. And the possible state of S, possible state in this problem is 0, 1, 2, up to, M, right? And let's say, all right, so 0, you order 20, 10, 8, and so on. So this is the actions. So that is the decision rule, right? So, for example, this table says, so when the number of unit at the beginning of the month is equal to 2, right? So that table tells you order, 8 unit. So if you could define the order quantity for every the possible state, all right, you can define this for every possible state. So you just define the decision rule. So this is the kind of example of a decision rule. And in this lecture, I'd like to introduce a policy with the two parameters, S under bar and S over bar. And assuming that this S over bar is greater than or equal to S under bar. And we call this is the SS policy. So this SS policy can tell you how much you should order for the certain state S. The decision rule says, right, this policy says if right, the system state is greater than or equal to S under var, you order nothing. So that is the delta S. And if S is strictly less than S under var, you should order S over var minus S. Or you order up to S over var. So this decision rule says the sufficient stock is ordered to raise the inventory up to the S over var units. So when the inventory level at the beginning of month is below the S under var units. So with these two parameters, you know how much to order for every possible state S. So with these two parameters, you should, decide the actions for every possible state, right? Unlike this table. All right, so far, we've discussed the basic component of the Markov decision process with an example. So we now discuss how to find out the value of the final horizon Markov decision model, process model. So the final horizon Markov decision process, the expected total reward, the policy pi, with an initial state S, can be defined as a function of U. So U represents the total expected reward if the decision maker follows the policy pi, right? This is the total expected reward. All right, and we wish to identify the optimal policy pi star, right, that maximizes these functions, right, these functions. Then, how could we find out the optimal policy? So as like the case of the dynamic programming, we will work backward from the last stage problem, and such a solution procedure is called the backward inductions, right? So how it works? So basically, for all possible state, we decide the best actions for them in the last stage, and then we work backward. For all possible states in the stage n-1, we decide the best action for them. Given that you know the optimal values of being in a various state at the last stage n, right? In the algorithm, we utilize the Bellman optimality equation since it is proven that the V1s is coming from the Bellman optimality equation is same as this UN as with the optimal policy pi star. Right? So we continue this process until we reach the initial state at the initial stage. All right, here is the details of the backward induction algorithm. Since you know the value of the Markov decision process of the state S in the final stage N, right? Vn star S is same as the terminal reward of the S for all S, right? So since you know all the values of the VNS, right? VNS star for every possible value of S. So by using this Bellman optimality equations, you can calculate, so let's say you know every possible value of the V at the stage N. By using these optimality equations, you can calculate V star n minus 1 for every possible state S. Again, since you know every possible value of the V star at stage n minus 1, by using this value, you can calculate V n minus 2 star for every state S. All right? So we keep doing this. You keep doing backward, and then finally we stop if t is equal to 1. Right? So as mentioned earlier, we can show that the optimal value at S is same as UN pi star S for every S. So pi star is the optimal policies, right? All right, so in the today's sessions, we learned what the reinforcement learning is. The reinforcement learning is a branch of the machine learning that allows the system to learn from the consequences of their own decisions. And next, we learned the basic component of the Markov decision process, including the stage or decision epoch, state, action, transient probability, rewards, and in addition to them, we talk about the decision role, policy, and value functions. And finally, we briefly learned how to solve a finite horizon Markov decision process by using the backward inductions. And in the next sessions, we're going to continue the discussion on the infinite horizon Markov decision process. Right, so that's it for today. Thank you.